Hello, I'm Gareth Funning, and I'm presenting the results of our research looking into the distribution of creep in California using a comprehensive INSAR dataset. This is work I've done in collaboration with Simran Sangha and David Beckett at the Jet Propulsion Labs. What we do is we take ARIA standard product interferograms. These are interferograms that are routinely processed from data from the Sentinel-1 satellite. We stitch those together. There's about 2,300 of them in our analysis, and track by track we process them through a time series software called MintPy and estimate the best fitting surface deformation velocity for each pixel. I've shown you the full data set here. The whole state of California is covered by 9 tracks of the Sentinel-1 satellite, 4 in the ascending geometry where the satellite's flying to the north, and 5 in the descending geometry where the satellite's flying to the south. And what we do then is we take these data, we take profiles through the data, and we try and estimate the offsets of those profiles and then solve for the creep rate from those. So in detail, we take profiles, and this is an example of a profile box. It's 2 kilometers, it extends 2 kilometers either side of the simplified fault trace I'm showing here, and is 2 kilometers long along strike. We collapse data onto a profile line, we fit lines to that data, and then we can invert it, the ascending and descending, the 2 different viewing geometries here, to give us an estimate of creep rate and relative vertical offset rate across the fault. This is the methodology we use. We take data from a profile, we blank out the zone around where the fault is mapped. We select these 2 windows of data and fit straight lines to them. And the difference between, and these straight lines have a common gradient, and the difference between the 2, the y-axis intercept of these 2 lines is the offset rate, and we use that then to estimate the creep rate. So here's one example of a profile offset. We have ascending track 137 and descending track 42. These have line of sight vectors that point in opposite directions, and so given that the motion on this fault segment is predominantly horizontal, we see a reversal of the sense of motion across the fault in these 2 different lines of sight. So there's negative line of sight offset in the ascending data and a positive line of sight offset in the descending data. And when we invert those 2 estimates with information on the fault strike and the line of sight information, we get a creep rate for this particular area of about 19 millimeters per year. So this map shows our efforts for the entire region of Central and Southern California, starting at the north at the start of the creeping segment under San Juan Bautista, and going all the way down to the Imperial Fault by the Mexican border. Each one of these squares is a creep rate estimate from a profile. They're spaced 2 kilometers apart, as I mentioned, and there are about 20 active fault segments that we have considered so far. In total, there are 1,300 estimates of creep rate. In this color scheme, red is right lateral surface motion or surface offset. Blue would be right lateral surface offset. We don't really see very much of that. And white indicates no resolved creep, and there's quite a lot of that. That's most of the profiles we tested do not show strong evidence for creep. Here we've zoomed in on the Central San Andreas Fault, and I'm not going to labor the point very long, but what we see on the Central San Andreas Fault is a very consistent moderate to high creep rates along the fault, rising from around 0 up to about 28 millimeters a year, and then down to 0 again when we enter what we assume to be the locked segment in the Carrizo plane. We also see some evidence for creep in Southern California. So the section of the San Andreas Fault that includes the Coachella Valley and the north shore of the Salton Sea, we see evidence for around 2 millimeters a year of creep in 3 potential segments, one around Indio, one southeast of Indio, and then one on the north shore of the Salton Sea. Down here on the Superstition Hills, where creep events have been observed, we see about 5 to 6 millimeters a year of creep. And down by the Imperial Fault, we could potentially argue for around 2 to 4 millimeters a year of creep, although the signal is rather noisy.